couldn't be. On the one hand, it was good because I was in Copenhagen and it was 10 degrees less than here. But on the other hand, I was sad to miss many of the great talks. I think it was a great conference. I'm going to tell you about this work that will come out in a couple of weeks in collaboration with Parra-Martinez from Lausanne. Okay. And it goes back to, well, actually, maybe before I start, can I show kind of how many people here think of themselves as mathematicians? Just to get an idea. Okay, good. Yeah. So sorry to all of you. So. So it's a theorem in the physics sense, but the idea is that we are trying to make progress towards actually proving it at this with our current understanding of quantum field theory, right? So of course, another theorem is one of the most famous theorems in theoretical physics that tells us that symmetries are intimately related with conserved quantities. Okay, and in field theory, actually, this has to do with conserved currents, right? In field theory, we typically have some conserved current whose integral or some kind of dimension one manifold gives us some quantity which is conserved. Okay, and so this was proven in 1918 by Nether and for classical systems, and it's kind of one of the backbones of our modern understanding of field theory. So there's this idea that symmetries are related to conserved quantities, and this essentially is the same as topology, the model perspective. Okay, and the proof of Nether's theorem for classical field theories is very simple. You just take the action of your theory, you perform the sum transformation, which will be your symmetry. Of course, these are symmetries associated to kind of Lie groups, continuous symmetries. So you can, there's a notion of uninfinite decimal transformation. And then this on shells, on the support of the equation of motion, the variation of this action is simply the integral of the variation parameter, yeah, I'll call it theta here, and then the differential of some current. And because we want this variation to be zero, this tells us that there is a conserved current. Okay. And and of course, to this we can associate some operator that generates the symmetry, which is basically the exponential of this current, theta, the integral of some dimensional manifold, is J. Okay, so here I will be talking mostly about zero form symmetry. So this is always dimension one. I'll comment at the end about higher form symmetries briefly, because I think most of the story goes through. Okay. Okay, so this is already a bit quantum. So in quantum mechanics, we say we do have this exponential, and then furthermore, this current satisfies some local word identity. Right? So in the presence of some charge operator, this current is conserved only up to some contact term proportional to the charge of this operator. Is at x, the zero. So there's a delta function contact term at the position of the operator. And again, this follows straightforwardly from when you have a theory with an action, just from the path integral formulation. It's a textbook exercise to prove these local word identities. Okay. However, for an abstract quantum field theory, so if I just tell you here is my theory, this is the spectrum of operators, these are the correlation functions. As far as I'm aware, there is no proof of this theorem. Okay? So we cannot really prove that if you have some selection rule on the set of correlation functions, some theory is associated with some continuous symmetry, that there has to be an operator in the spectrum which is a conserved current which satisfies such local word identities. Okay? So what is the actual statement of this Nether's theorem in this modern language? Is if I have a continuous family of, and for this talk, I'll just talk about invertible symmetry. So vertical, topological, into dimension one will be zero form symmetries, operators, topological, yeah, operators. This implies the existence of a current a picking or local operator in the spectrum, which satisfies the whatever. Okay, and yeah, so the idea is that this operator acts on this kind of object will act on local operators. Just wrapping them. So if I here have my operator, then because it's conserved, so this is topological, and I'm able to deform it a little bit, so the correlation functions don't change as long as I choose some other manifold which is homologous to this, and I don't cross any other insertions. And in fact, this is the same as e to the I theta q times the insertion of the operator. Okay. So this is the assumption that I have this continuous family. For most of this talk, also I'll restrict myself to a usual U1 symmetry for simplest.
Julio?
Yes.
I have a feel free to tell me this question is too mathematical, but as you said you're approaching rigor. I'm curious, what kind of object mathematically are you planning to construct here? This J? I asked that because like a field in a time correlator satisfies word identities, but an operator in like a white function doesn't have the word identities, has exact constant.
Yeah.
So I kind of wondered what you're trying to do.
Yeah, so it will be more clear in a second because I'm going to go to conformal field theories. And then in the realm of conformal field theory, everything is much clearer. I have some set of local operators with local operator product expansions. And then I'm just looking for some particular operator that satisfies certain local OPs with other operators. Okay, any other questions? No? Now let me see if I can. All right. By the way, just a side comment. So this idea that symmetry is topology, of course, another theorem is behind this. I recently learned, maybe mathematicians know, I think most physicists don't know that it was Nether herself in 1925, that on a 14-line comment in some very, very long book, she pointed out that this thing that people were calling like Betty numbers and torsion coefficients were just the dimensions or like orders of certain abelian groups. So I think she was already onto this idea that topology and symmetry are basically the same. Okay, so the idea is to try to get the dream would be to try to get a general proof of this statement for general abstract UFTs. Of course, I need to choose some framework to do that. And I think something important is that any proof needs to impose some notion of locality. So this has to be very important. And this is because we know that there's could be counterexamples to another theorem. So for instance, if you take this thing that is called the generalized free field, so this is a theory where you have a bunch of local correlation functions that satisfy consistent OPs, but there's no stress tensor. So in this case, there is no stress tensor operator, a very special operator, so that we know how to do infinitesimal homomorphisms. Then we know that this you can have a symmetry without carbon. There's other stupid counterexamples. So for instance, if you have like n copies, non-compact theory. So basically a bunch of copies of R gauge theory or non-compact boson. Then you can also get violations of those. Okay, so we need to impose a suitable notion of locality. And people have tried. So for instance, there's this particular approach to quantum theory, which I'm not an expert in, but I will try to explain at least what the statement is. Yeah.
But if the counterexample is the non-compact boson.
So in a non-compact boson, for instance, if you take a non-compact boson, two copies of the non-compact boson in 2 dimensions, I mean, that theory is already a bit funny because its partition function is infradivergent. And then you can check that there is something that you can call a current, but its correlation functions will be logarithmically divergent. So they don't satisfy the usual properties that we expect from local correlation. In higher D, then if you have like a bunch of copies of R gauge theory, say in 3D, then you can have some continuous symmetry, some orthogonal symmetry that permutes them. So say you have 2 copies of R Maxwell. There's an SO2 symmetry that rotates one into the other, but the current is not gauge invariant. So there is no conserved current.
So then,
yes.
Why is the first I was thinking boundary level. I thought you looked about kernel symmetry. So it's maybe not in the power window sense.
The issue is not that there is no stress tensor, is that you can find internal symmetries for which there is no current. And we'll see that actually in my arguments, the stress tensor will play an important role. So assuming that the stress tensor exists, will be one of the inputs from locality that I will require.
The theorem is strictly about kernel symmetry.
Yes.
The current doesn't actually.
Yes. Yes. Of course, we also believe that something similar is true for space absolute, but that's not true. Okay, so just very quickly, so if you listen to some talks about this business, there's people that talk about this algebraic approach to quantum field theory, where they say that some things have been proven. For instance, there's what they call the weak version of another theorem. So these people talk about some like algebra of operators which are localized in some region. And then they say that if you take this algebra, you have some continuous symmetry, you need to choose some buffer. Okay, so some epsilon neighborhood of this. So there's also kind of an algebra which is for the complement of, okay, so this is some region sigma. There's the complement of this union, this epsilon neighborhood. And then they show that within the framework that one can indeed implement locally the symmetry. So you can find some local operator which is supported in here and in here. Sorry, not some local operator, some extended operator that implements the symmetry locally. However, this what I call the strong version, which is that currently exists, they cannot prove. Okay, so they have some notional locality, which they call the split property, with which they can prove this, but they cannot keep going and prove that the current actually exists. Okay. So in this talk, instead, I'm going to be more conservative. I have to confess that I don't really fully understand this algebraic QFT framework. I think there's something I understand, which is two-dimensional conformal field theories. So in this talk, I'll just stick to the usual axioms of conformal field theory. And since these are the axioms that we use in the business problem. Okay, so what are the things like? Okay, there is a unique vacuum. And stress tensor. We have a discrete spectrum. Unitarity. You could relax some of these things, but it turns out that these assumptions will be important. Yes.
If you, in terms of getting, would you be satisfied if you could say that all of these topological operators connecting symmetry could be divided into arbitrarily small pieces?
No.
Would you consider that having a current?
No. Coming current is having a local operator in the spectrum that satisfies the local order. So that's why this is not enough. Yeah. Okay. So actually, let me add the stress tensor here, and then I have like unique stress tensor. New, and then cutting and gluing for modularity. In fact, these are the notions of locality that will be important. Okay, so I'm going very slow, but I'll try to explain that using this in 2D CFT, we have a constructive proof. Means that we start with this continuous family of topological defects, and I'm going to explain to you how to extract a current, which will be an ordinary local operator that will satisfy the local world. Okay, for d greater than 2, I won't have a full constructive proof, but we can prove that there is an equivalence between Noether's theorem and the existence of 4-dimension 2 twist or monodromy operators. Defects, sorry. Which means that you have some dimension 2 kind of endpoint or end surface of my topological defect, which is conformal. And then from this, we can extract we can extract a current. Okay, so you can imagine if you believe that this is true, then you can just flow to the IR, and whatever this epsilon neighborhood is, it will just flow to some conformal defect, and then from then on we can extract the current. Okay. So, any questions?
Equal to you are not making additional count.
Sorry?
Equal to you are not
No.
making.
No, in equals to 2 is proved by the book with the usual. If you open the Francesco, if you read, if you learn 2D CFTs from there, then you can carry out the proof.
Then once you know that with the current, you can clearly prove that there is a amount.
Yeah, so in one direction it's trivial, right? Because you just do this exponential that I wrote there, and sigma can have a boundary, okay? And you can prove that is a well-defined conformal defect. What's hard is the hard, slightly harder is the opposite.
Sorry,
Yes.
they're able to prove it conformal to theory.
Yeah.
You say that apart from theory, just the information that.
Yeah, I'll comment about this at the end if I have time. But that's the idea. We should start at the fixed points, and then that's what happens on our. Okay. Okay, so let me start in 2D. 2D, we just have this U theta. So this is some topological line in 2D. Okay, so it's dimension 1. And of course, something that we can always do is we can study the partition function d theta theta, which is just the trace or the usual Hilbert space in the circle of e to the minus theta h with the insertion of d2 theta. This is, we have the torus, and then we have this line going in this direction. You can think of this as line. Okay. But of course, by modularity, we can just do a modular transformation. This partition function. And then we know that this is the same as the trace on the twisted Hilbert space, right? So this is in the circle, but it's twisted of e to the minus theta bar, which is just the usual modular image theta h. The picture here again is the usual one, where I have my torus, but now sorry, this is transverse to the time direction, and now it's along the time direction. Okay. Right. In particular, there is this Hilbert space. And in particular, there's a ground state of this Hilbert space. And if the spectrum is discrete, particularly there will be in the neighborhood of theta equals 0, there will be a gap to the next state. So nothing funny should happen when I send theta to 0. In fact, we know that the partition function is smoothly interpolates to the usual partition function of the theory. So this as theta goes to 0, you just get the usual ground state. By the theta operator correspondence, this is just the identity operator. And this will be some twist operators. This is some v of theta, which lives at the end of the line. Okay, so in 2 dimensions, these lines can end. And end on some actual local operator is v of theta. Okay, so that's the analog of this conformal. Yes, I raised this conformal monodromy defect in 2D, which is just an ordinary local operator. Okay, so with this we'll just construct the current. Actually, it's very simple.
Sorry.
Yes.
Why the ground state of the efficient space?
It's unique because we assume that there's a unique ground state for any Hilbert space. Yeah, by assumption. Okay, so in particular, this also means that this just becomes the identity when you send theta to 0. So how do we construct a current starting with this guy? Okay, so what are the dimensions of this? So I have h theta, h bar theta. So these are the eigenvalues of the two kind of L0, L bar 0, the two kind of level 0 beta soror generators.
How when the assumption of the sweetness of effect when you enter is a
So funny things can happen if you don't have a discrete spectrum because you don't have a well-defined notion of the ground state. And for instance, there can be level crossing and stuff like that. And we have examples actually where this happens. So in fact, these logarithmic examples, these ground compact examples, this is what happens in that case. So you have a continuous spectrum, and then there's some non-analyticity in theta, because there's some level crossing at theta that obstructs taking all of these limits smoothly. Yeah. So all of this in the paper will be explained in more detail, but here I just want to give you the general idea. Okay. Something else that we know is that because it's invertible, actually the diagram of this thing is just V of minus theta. These two operators are Hermitian operators, which means that actually these are symmetric, and that's theta going to minus theta. Okay. And because this goes to infinity, this has to start a quadratic order in theta. So in fact, these dimensions are something like k/2 theta squared plus higher the corrections, same for each part. Okay. So in particular, they vanish as theta goes to 0. Okay, so now with this twist operator, we will just directly check the current. I'll tell you how we define the current, and then I'll tell you, check that this is a well-defined local operator that satisfies all the properties. So our definition of the current, so we're going to use the existence of the stress tensor. We have that if you take the OPE of the stress tensor with this, there will be a double pole, tells that this is some conformal primary with this weight. And then there will be a non-singular piece, which is well normalized, which is the first descendant of this. And this is not a primary on the Hilbert space of the on the local operators associated to the endpoints of this line. This is not a primary; it's just a descendant of the ground state. Okay? But this has a nice property, which is that if you look at this theta, h and h bar, this is because this is just essentially a derivative, holomorphic derivative of this theta. This is just a shift by 1. Okay, and in particular, when you send theta to 0, this becomes a 1-0 operator, which if this was a well-defined primary, then automatically by unitarity, it would saturate the unitary bound and it will be a conserved current. Okay, so we just need to check that that this is a and from this we can get a well-defined primary. In fact, the definition of the current will be a holomorphic current is the following, which is the limit theta goes to 0, 1 over theta d theta. Okay, so this limit has to be taken inside of the correlation function. Okay, so you start with some correlation function with this primary, you take a derivative, compute the correlation function for d theta, you divide by theta, you take the limit, and we claim that this is well defined, and then it gives you a current. So the intuition is that you have this thing that live at the end of the line, okay, and then if you hit endpoint, which is the of theta with the stress tensor, inside of here, there will be this d of theta, which just means that this has moved a little bit compared to this kind of infinitesimal translation, which means that if you think that this line came from integrating a current, this should give essentially the current. So when you send theta to 0, this will give some well-defined local operator. Okay, so to make sure, we need to check that that it's a primary, that it's actually a well-defined local operator. In particular, the limit is non-trivial, and that it satisfies the correct word identities. Yes.
You can assume somewhere that the spectrum contain multiple operator for minimum together.
Yes, yes. So I didn't say this, but of course I want the symmetry to act on the spectrum of local operators. So it has to be. In fact, we mentioned that it acts faithfully. If it didn't act faithfully, it could be that the operator can end on a topological point operator, and then the argument doesn't go through. So
Then you can take this limit well defined by zero.
yeah, so that could happen if it doesn't come. But in fact, the 2-point function, I'll show you in a second, that actually is not zero. So, but you need to check all the correlation functions, and we check all of them, and indeed it satisfies everything. So let me just give you a flavor. So how do we check that it's a primary? We just take this OPE, you take a derivative, right? Because the OPE converges like exponentially well. You have a split spectrum. So we just take a derivative with respect to the position of this operator, and then take this limit. And then if you do that, you just find. Okay, I was planning to do this calculation, but I don't think I have time. So you just get the P and this data as the expected form. So this is like Z squared J plus 1 over C J, which is just the OP for a conformal primary, which with dimension hallmark dimension 1. Yes.
Well, what sense is how does that limit? Why does the limit exist, and how is it defined?
So it's defined by inside of correlation functions. Okay, so I start with a correlation function that contains this descendant, and I'm going to define the local operator by taking a limit of this correlation function, which is this picture here. And the fact that it exists actually relies on the fact that we expect that. I mean, you can either say that the spectrum is discrete, so we don't expect any non-analyticity as theta goes to 0, or just assume that things will be analytic. That we think that this is equivalent to this.
Some part of series that the limit or family of correlation exists, and the well-defined operator.
Well, we.
So it's not like limit the follow.
So the correlation function exists for any value of theta, right?
Right.
So
why do it say that it exists and to some operator?
Well, if you wish, we actually checked. Okay, so if it's a proof by actually checking that under these assumptions, we can check that in any correlation function the limit won't be singular.
Well, but a limiting correlation function exists, but why do you know that there is a local operator which reproduces this limited correlation function? So it's about the meaning of the limit.
Well, the thing is that this endpoint is not. It's almost a local operator, right? So this is not a genuine local operator because it's attached to this line, right? So if the limit exists, this line becomes the trivial line, right? So either this operator disappears altogether, that's what happens if you don't divide by 1 over theta, you just get 0, or it leaves behind some local operator, right? Because this line becomes trivial. We're in the neighborhood of the identity, so. Yeah. So this already depends on this position. So if the limit exists, then this will look like the correlation function of a. How much time do I have? 12 minutes. Okay. So let me just tell you what else we've checked. So we've checked that if you think about now the 2-point function of this, which you can define by starting from this, taking derivatives at both endpoints, and just taking the limit, you do get that it's JJ equals K over V squared, where K was that K over there. Okay, so this is again the and by the way, by unitarity, this was positive, so this is non-trivial. Okay. We've checked that all limits in 3-point functions in the presence of a third operator, they're well defined. One can always take the limit, and it looks like a 3-point function of the current with maybe some third operator, which is here. We have even shown that if you shrink this segment in the OP of B and B dagger, that in here, so that's for small theta, we just have this J and J bar. So J bar is the same thing, but with anthropomorphic descent. Outside of it. Okay, so this is just directly in the OP of these two without taking any limits, because we can show that it has non-trivial correlation functions with this with the right form. And once it's in the OPE of this, then it's clear that it's a well-defined local operator because all correlation functions satisfy crossing in the presence of these two by assumption, because I started with a well-defined theory, then also it will satisfy this J and J bar. Okay, so
what I understand correctly that you were saying that if this limit exists, then all the correlation function involving J satisfies all the nine.
all the bootstrap axioms.
All the bootstrap.
Yeah,
Rather
so
than
that's what we
saying
should.
that is not immediate.
That doesn't mean this limit exists, but if this limit exists, it satisfies all the axioms, and we believe this limit exists as long as the spectrum is discrete and the gap doesn't close until 10 theta to 0. Yeah. But if you wish, we have to assume that there won't be any non-elasticity. Yeah. Okay, so let me just tell you very quickly how we do it. Okay, so the word identity is very similar. So we just need to use the fact that I don't have time to explain that we start with the correlation function, with this V theta and the dagger theta, then some third charge operator. And then we know that when we take this guy around, by definition of it being charged, it needs to pick up the right transformations. Okay, in particular, that means that in the OPE of this, with this guy here, there will be an operator whose the difference between the spin of this and that operator will be precisely Q theta. Okay. Then if you use that and you use the definition, you just land on the usual word identity. I don't have to do the time to do the calculation, but you find that. So if you wish in yes, I'm sorry. Explicitly. So that's it. So it is non-trivial, it satisfies all the bootstrap axioms. Okay, so as far as I'm concerned, a perfectly well-defined local operator that satisfies all the properties that we want for a current. Okay, let me say now some words about d greater than 2. But ideally, in d greater than 2, we would like to do something similar. However, the equivalent of this twist operator won't be a local operator. It will be some dimension 2 operator. I don't know how to prove that this exists. So, so the best we can do is we can assume. Okay, so we will assume that there is this dimension 2 conformal defect. Yeah, that's fine. That just means that the endpoint is charged under the U1, but it doesn't matter for.
It's
just that K, there's this K that I introduced. There's a K bar for the other. They will be different, but that's the only thing. There's no requirement that K and K bar are the same. Yes.
You use compactness of the symmetry and
we use compactness of the symmetry. Well, we use discreteness of the spectrum. Let me see, did we use compactness of the symmetry? I don't think so, but maybe secretly somewhere we're using it. I have to think about it. Yeah, I have to think about it. It could be that implicitly we're assuming it in somewhere, but I cannot tell from the moment. We assume that it acts faithfully. I don't understand.
It's not complex symmetry that acts faithfully, it acts faithfully on the screen.
Okay, there you go. Okay, so as I was saying, in d greater than 2, ideally, I would just assume the usual bootstrap axioms for local operators and to prove somehow using crossing that this current exists. I won't be able to do that. Well, I've tried. I think no one so far has succeeded. So I'll just assume that there is this dimension 2 conformal defect that this topological operator can end on. And then again, if you take some local operator OQ, and then you just take it around, then it will pick up this transformation, okay, which is just a definition of this mononomial effect. And basically, we are assuming that this is a well-defined conformal effect. Okay. So, for instance, you can think of this, yeah, the higher limit of that twist that the AQ is talking about. If you map it to hyperbolic space, it's the same as assuming that the symmetry acts properly on the Hilbert space on HD minus 1. Okay, so there's a conformal transformation that maps this with just hyperbolic space with this defect, just my colors. Basically filling some HD minus 1 slice, right? Which is also assuming that there's a kind of symmetry preserving boundary condition here for the defect. So it seems that it's a reasonable assumption. I don't know how to prove it, but that's what we're going to assume. And then the role of this descendant, again, we use I'm just going to tell you what is different from d equals 2, because most of the proof is the same. Once you have this conformal defect, then you can just take the stress tensor, and then you can take the OP with this, and then famously in this OP, there's a protected operator. Right. So if I take kind of x parallel 0, then there's just a C number term. And then there's this operator, which is called the displacement operator. Dimension is b minus 1. And so this basically under the symmetry, which is preserved by the defect. So again, let me just do a conformal transformation to make this a flat defect. So this preserves an SO b minus 1 over 1, and the transverse rotations around it. Then this thing is a scalar dimension b minus 1 here, and it's a vector of the SO2. Okay, so it has some nice quantum numbers. And basically this is called the displacement operator because it parameterizes what happens if I do an infinitesimal diffeomorphism of this mass, of this dimension to. So there's a bunch of water entities that it satisfies based on that. Okay, so this is the key object that we use to define the current also in higher dimensions. In higher dimensions, we define this fugitive current. Again, it will be the limit when this goes to 0. It's because that when it's introduce the epsilon tensor for the transfer states, there's an I. The I was also there in 2D. The epsilon was there in 2D, but because I was using holomorphic and anti-holomorphic presentation, then you couldn't see it. So for instance, you can check that indeed, if you take just your conformal defect defined as the exponential of the current, if I take this as the exponential of like I theta star j, where this sigma has a boundary, then this relation is satisfied. So in one direction, it's very simple to see that this is true. But then we just need to check again that if the limit exists, which we think it exists, as long as you have a discrete spectrum, that then this will define a well-defined local operator. So we did basically the same checks as in 2D, and they all pass. The only subtlety is that to prove that it's a primary, one needs to be careful, because when I take the limit, this will give me a local operator. So given these quantum numbers, we need to analyze what are all the representations of the full conformal group that branch into this. Okay, so it's a very tedious exercise because you have many representations. You can do partial traces over the process directions. At the end of the day, what we find is that this Ji can only be a linear combination of two objects. One is an actual primary, so a conserved current. Again, by unitarity, this will be a vector for the full conformal group now. So S of B plus 1 to minus 1 with dimension -1. So it saturates the unitarity bound, so automatically will be conserved. But it could also be some transit derivative of some scalar with dimension B minus 2. Okay. So this is not ruled out just by the representation theory of the conformal group. So we need to work a bit harder, but there is an argument that rules this out. And again, we use conformal symmetry. So the basic argument is that we think of the correlation function, the 2-point function of this displacement operator, but on a spherical defect, not on a flat defect. So on a flat defect, these two things, we cannot distinguish the correlation functions. Finished? Okay, so I'll just say it in words. By considering the correlation functions of the displacement operator on a spherical defect, and you take the limit and you see that that is only compatible with the 2-point function of a current, and it's not compatible with the 2-point function of a descendant of some scalar of dimension B minus. So that means that only this current is allowed, and it's a primary and it's conserved. And again, we can show that it satisfies the local ordered entity. So we think it's a good definition of the current. Okay. So open questions is basically okay. So we did this for a U1 symmetry. I think for non-abelian symmetries, the same thing is going to work. One can just work one generator at a time. Nothing is very different. For higher form symmetries, in fact, it's a bit easier because this branching problem that I just described, which was kind of very painful for the zero form symmetry, is simpler. So in fact, one doesn't even have an analog of this that contaminates the problem. So we won't do it in the paper, but we believe the same thing would work. Okay, some questions is space-time symmetries. Here, I don't know what to do. I assume I have the stress tensor, then I'm done. So, new ideas are needed for space-time symmetries or non-invertibles. There's a couple of steps that don't work. Can we prove the existence of this monotomy defect in general? I don't know how to do it either. So observation is that this gives a constructive way of extracting this current. This could be useful, for instance, in lattice models. If you have a lattice model, okay, that just very quickly. So if you have a lattice model where as you flow to the IR and you know approximately how the symmetry will act in the UV, even if it's not a symmetry, you can always construct this monotomy defect in the UV and flow to the IR. Okay. And similarly, I think it would be interesting to think about RG flows. Okay, I'm out of time, so I'll stop.
One quick question. Jonathan? Say a little bit more about the non-countable breakdown. Why can't you allow a UHD to be on the?
So basically, what we needed, I don't know if I say this, but we needed the existence of this conformal non-invertible defect. Then when this becomes trivial, it also becomes trivial. Okay, so even in 2D, you see that if you have a non-invertible symmetry, there is no guarantee that there's a neighborhood of the identity, that there's some family which is continuously connected to the identity. So so we don't even know that we'll actually land on some genuine local operator. But we know that the counterexamples could be something like a current living at the end of some topological line. So maybe it's okay, at least in the equals to. In higher dimensions, I have no idea.
Okay, thanks again,
No, it's going to get slight. Thanks.
Yes.
Okay.
Yes, I'm really happy. Also, I can think you speaking this one place, this is a nice happy house.
I thought I already took off.
Right on. Something like that. So this one is the microphone overview. And in the front, you can box it in something. Yes. Should work. Yes, it should work. No, put it in the in the box. Yes. That's better. Yes. Sounds good. And this one. Then the pointer is here. Is the pointer. And but we had a different one, and this one doesn't work for moving the slides. So you have to do
The point is, yeah.
the pointer.
Okay, so our last speaker, Jonathan Heckman, will be telling us about SWAP.
Okay. So first, let me say thanks very much to the organizers for putting this together and giving me the chance to talk. And since I guess I'm the last speaker, maybe we can all thank the organizers for putting this together. Thank you all for showing up for the last talk in this kind of hot room. Okay, so what I'll tell you about today is some work related to TFTs, and in particular something that I don't think has been talked about too much at this conference so far, which is things connected with gravity. Julio already apologized to mathematicians. I'll apologize to them. I'll also apologize to people who don't like thinking about gravity. So probably almost everybody in the room. I'm sorry, but McKelly told me not to talk about some other thing that I was planning to talk about. So I'm not going to talk about that, and I'll talk about this instead. Okay, so this is based on a paper that came out with Charlie Cummings, who's a graduate student at Penn. He's applying for jobs in the fall. And it's also based on a series of papers that written over the last few years with some combination of people both in the audience, outside the audience. I just want to give a little bit of background about this whole set of papers and all that. Okay, so as you all know, quantum field theories are very nice in describing many systems that have lots of degrees of freedom. Usually one has some notion of locality to leverage the structure of quantum field theory. And from this point of view, TQFT, they're just a nice special case. So for my purposes today, they're just going to be something that's a nice way to characterize certain kinds of theories that have a gas spectrum. And this, of course, shows up in certain kinds of symmetry operators where we imagine we have some sort of TFT and it's coupling to some ambient fields, bulk QFT. Okay, so here's a question. How big can the energy gap be? That we want to talk about. So a nice way to think about it is I go below some scale, and below that, all I have are the topological degrees of freedom. There's no particle-like or local excitations. How big can I make this gap? Push it up all the way. Can I formally push it all the way to infinity? Okay, now there's a general claim, and I hope this is not too controversial, which is that there is kind of a cutoff on how high we're allowed to push it, which is this scale set by the so-called Planck scale. So in 4 dimensions, that'll be around 10 to the 19 GeV, which is far above anything we would talk about kind of everyday experience. There's a more kind of qualitative reason, which I'll try to sharpen. So I'll try to make this much sharper. So there's a kind of vague statement that you'll find in many papers about why you should expect something like this to happen. There's no sense of topology when you get to these very, very high energy scales. So even the notion of space and time that you want to talk about starts breaking down. So what could you even mean by talking about topology and defining a field theory on a fixed manifold or anything like this? Now this is incredibly vague, and I'm not going to do this. This is supposed to be what's called quantum foam. I have no idea how to make sense of that. So what I'm going to do instead is try to make this a little bit sharper. Of course, this is also, there's an implicit theme that TFTs have a lot to do with global symmetries. And kind of the lore that's developed, at least in the context of gravity, is that, no, not really. You don't have any global symmetries in quantum gravity. Rather, as you go into the low energy degrees of freedom, you'll start seeing emergent global properties start to emerge. So the kind of slogan that people like to say is that symmetries are either gauged or broken once we start including gravity. Okay, so another motivation along these lines is in the context of black holes. If we have, say, charged objects of some kind and we throw them in, question is, what happened to all of your beautiful global categorical symmetries in the presence of, say, non-trivial backgrounds like, say, black hole? And there's various different kinds of thought experiments involving both black holes, refrigerations, things like this. I'm going to try to sharpen this in a particular way, but a just motivating question here is, what happened to all these wonderful global symmetries? Something interesting is going to happen. It's not like I'm saying it's worthless. It's, of course, very, very beautiful. We're going to instead see how things get modified. Okay, so here is where swampland appears. So what is the idea here? The idea is that if I give you a quantum field theory without gravity, and I try to couple it to gravity, the general expectation is that some kind of non-trivial constraints will show up. Now, the way this comes about in practice is people start with, say, a place where they think they understand something more about quantum gravity, say string theory or holography, and they just ask, if we start taking limits where we have a quantum field theory sector, can you get any kind of quantum field theory like, or do there appear to be different kinds of constraints? Now, of course, that's a little bit self-referential. You'd like to be able to kind of start at low energies and say, what is admissible as you start going to higher energies? And so the idea of the swampland is somehow that there's a nice pristine area where you can go all the way up into the ultraviolet. And then outside of this is where it's a little bit dangerous to do that. So an example of a swampland constraint would be that there's no global symmetry. Okay. Okay, and here's a picture of his collaborators, hard at work. Okay. So what am I going to do in my talk? I'm going to talk about trying to sharpen this in the context of gravity, in particular this celebrated ADS-CFT correspondence. This is an idea that certain kinds of quantum field theories, conformal field theories in particular, can be related to a dual gravitational description in higher dimensions. And what we're going to do is interrogate the question of what happens to all the global symmetries in, say, the boundary conformal field theory from the point of view of the gravity. And can we tolerate having global symmetries in this gravitational theory itself? So what I'm going to do is we're going to set up a thought experiment. We're going to take the standard ADS-CFT correspondence and we're going to extend it by adding in an additional sector. We're going to add in a TQFT, and this TQFT is not going to couple to the metric degrees of freedom, except possibly at the level of the topology of the space. Now, perhaps not surprisingly, what we're going to see is that, of course, there's going to be some kind of non-perturbative coupling. So by that I mean it goes up as some exponential in Planck scale divided by energies. That's not too surprising because we also know in gravity we're supposed to sum over different kinds of topologies. So if I give you a TQFT, the question is, does it still make sense if I start summing over multiple different kinds of topologies? Perhaps more surprisingly, when we set up this thought experiment where we take the standard gravity and add TQFT to it, there will also be a linearized coupling to gravity. So the breakdown is going to be more severe. And I'll walk through why this appears to be happening. So initially, this is perhaps the not so shocking statement. The perhaps more shocking statement is that actually the fields of the TFT know about gravity a little more strongly than you might have initially thought. It's a little bit hard to define this in all cases, but it's a situation where I know it when I see it. In many of the cases, the TQFTs that we talk about are going to have fields where they pick up a kinetic term that starts decoupling once we go into the infrared. So I'll give you a couple basic examples as we go. But the point is that everything that you have from the field theory, the TQFT is kind of embedding inside of a bigger system. As you'd expect, if really there was this gap and there was some kind of limit to how big the gap could get. Okay. So what I'll do is first I'll kind of lay out a top-down perspective. So how we're thinking about kind of symmetry operators from the point of view of both gravity and in string theory constructions. And then I'm going to switch gears and kind of approach it from a more bottom-up point of view, saying these are some nice lessons, but can we kind of argue more broadly and more generally without making, say, certain assumptions, say, kind of like the loaded baggage of string theory. And what we're going to then see is how this fits with gravity. Okay. Okay, so here's the top-down perspective. We're going to start with gravity and then try to take a limit where gravity is decoupled. We're going to ask whether we can see all of the nice symmetry operators that everybody else has been talking about come out from such a frame. Okay, so there's different ways of doing this. There's a very old way, which is string compactification. This approach has been around for, I don't know, 40, 50 years, who knows? Holography, which is this idea that there's some gravitational system with negative cosmological constant, anti-de Sitter space. The boundary is CFT. ADS is here being represented as a giant cylinder. This is the Lorentzian signature version. I'll be talking about that version and the Euclidean signature version. Interestingly enough, there's a way to kind of access these questions through so-called cobordism conjecture of McNamara-Vafa, not the other cobordism hypothesis, but and then directly from, say, looking at how strings experience, say, the ambient target space geometry. So what I'm going to do today is just focus on these two. And this you should kind of use like motivating what I'm going to do over here. But just kind of to explain, this is how we saw a bunch of these structures emerge, and then we wanted to ask the question more broadly outside of the world of string thinking. Okay, so string compactification. Okay, so what's the idea? You take various long distance limits to hit various kinds of quantum field theories in the infrared. And one particular way of doing this is imagine you have, say, a Calabi-Yau cone of some kind with some localized singularity, and then a quantum field theory of interest might be locally realized over in this little tiny region. And then the 4D spacetime is where our quantum field live. It doesn't have to be 60 extra dimensions, by the way. You can change who is 4 and who is 6 depending on what you want to do. Okay, so let's say you start with like a compact six manifold like this, and you have both the local degrees of freedom for the field theory as well as gravity. Well, Newton's constant in the 4-dimensional theory is basically controlled by the volume of this extra dimensional manifold. So as you make it bigger and bigger, the effects of gravity get switched off. Okay, so this is just kind of the preliminary starting point for making a quantum field theory. Now, where are the things like symmetry operators, defects, and all that beautiful stuff happening? Well, they're coming from both frames and also certain kinds of singular geometric configurations, both for, say, making a line operator, for example, and the symmetry operator, the one-form symmetry operator, which might act upon the line operator. So how does that work? Basically, the heavy defects are just frames or things like it that extend radially out from the tip of the cone or wherever you made the field theory out to infinity. There is now a notion of infinity because we decompactified the whole 6 manifold or whatever. And then the symmetry operator is enacted by a linking both in the space-time direction as well as in the boundary geometry off of infinity. So if you want an example to keep in mind, take like, say, C3, the orbital fold C3 mod gamma, and then off at infinity, we have S5 mod gamma. And there's a linking that takes place between the symmetry operator piece. So this story I'm telling you here is now about 3 or 4, maybe 5 years old. And you can do more things, like, for example, read off the TFT associated with the symmetry operator straight from dimensional reduction of the brain action. Here. Okay, you can also get things like the symmetry TFP and symmetry theory by basically doing dimensional reduction along with linking geometry. And this has also been worked out in several papers. In fact, you can even work out things like the coefficients for the couplets in these TFPs by looking at, for example, the eta invariance associated with this boundary geometry, as well as variations on that theme. So a matrix Quiver-Hilbert series, which basically finds another way to kind of count the degrees of freedom relevant for figuring out the anomaly coefficients. What I mean is you take all of the fields on X, and then we look at a basis of fields, and then we basically do the naive thing where we just start integrating over those directions. So all the fields are 10-dimensional fields, right? So what I want to do is just integrate over that boundary X piece. That's what I mean. So you can view it as like averaging and so on. Now, if you do this for the full action, it gets a little bit poorly behaved, but at the level of topological linking numbers and things like this, it's much better behaved. So it basically just reduces usually to things like intersection theory for linking numbers. So it's pretty insensitive to a lot of that. Okay, so how would you bring gravity back in? Just stick a cap on the whole geometry. Obviously, this is not really what it looks like, but it's morally speaking this. Newton's constant is now finite, and all of the things that we had before that were just nice topological things and just rigid, heavy defects or whatever suddenly come to life and they become fluctuating dynamical degree. So the general lesson from this point of view is that the symmetry operator itself becomes a fluctuating object, dynamical brain, by the time we start talking about it in the full-blown theory with gravity included. Okay, so can we see that without necessarily invoking the special cases associated with string theory? Can we see it from a more general point of view? Indeed, you can. So there's this general law again, that part of the ADS-CFT correspondence tells us that global symmetries of the boundaries CFT correspond to gauge symmetries in empty de Sitter space. Question, what does this mean for all of the wonderful symmetries you guys have all been talking about this week? What do you want to do for the analog of this in the context of these much more complicated and involved global symmetries? It's really been worked out fast for the case of this continuous zero form symmetries, but what do you want to do in this broader setting? So the other thing that I'm going to use is that basically as you move into the interior, that goes from here to here, moving into the interior basically corresponds to, if you like, smearing out or kind of coarse graining the whole thing as you go from the ultraviolet down into the infrared. Okay, so yes, please. Well, there's of course examples like 3D Chern-Simons and like chiral edge modes and things like this. But the point is here, it's really gravitation. So the case that I know that's morally speaking as close as possible to this would be where it's not really, let's say, a local quantum field theory on the boundary. It's like a little string theory or something like that. And there in the bulk, you don't just have gravity. You have like a linear dilaton background, which is blowing up as you go to. There's far less control in that situation. Those are kind of the two situations I know where you can kind of do this with gravity. Of course, it's a very nice thing to do. Like the topological holography point of view is part of this bigger thing. And from that point of view, right, where's the sim TFT and all that? It's this little sliver here. And so basically the physical boundary condition is here. And then once you take the large N limit and take the gravity dual, it's kind of melted away and turned into this gravitational thing. You still have the topological boundary condition up here, but this is where the physical boundary condition used to be for, say, the sim TFT or the symmetry theory. Okay, so how does it work? You can take your symmetry operator here in the boundary. That's supposed to be all the way on the boundary. And we start moving it first into the sim TFT region, and then all the way into the bulk. Okay, now I've suggestively made it go from dash to solid. What could that mean? Well, the expectation is it's turning into this dynamical object as we push it into the bulk. Now, how does this work? Well, we've already explained from the top down. There are many examples of ADS-CFT that come straight from string theory, where you start with a brain and you push it into the boundary. That's actually the story I was just telling you about on the earlier slides. That part of the story seems pretty clear. What you do in that direction is you're taking somebody who's a bulk dynamical brain, push it into the boundary, and all of the local fluctuations start freezing out. All you're left with is the topological remnants. But those were specific examples. Maybe I don't like those examples. Maybe there's examples of ADS-CFT I can't get from string theory. How would I argue more generally? So the idea is to use smearing. So imagine you have your symmetry operator, and it's acting on some operator charge under it. And what we're going to do is ask what happens to this linking as we start moving into the bulk. We start smearing it out. So here, you could say, oh, is U acting on O? Well, it hasn't shrunk down yet, so it's still a notion of O versus U being distinct objects. But as you go into the infrared and you start smearing all these things out, the distinction becomes harder to define. And eventually, the symmetry operator is just acting for sure on this thing. Why? Because it's just, this thing is fattened out to this point. What are you doing at this point? You basically are picking up a jump in the operator, or the bulk dual of this thing. And this jump corresponds to basically introducing some local source of stress energy, right where it goes from being the individual O to that. So essentially, it's a proof by contradiction style argument. You say, suppose it didn't have a tension or anything like that. What would happen? Well, there is in fact has to be a tension as it jumps from one operator to another. Okay, so statement is then, both from the kind of bottom-up point of view and also from the stringy point of view, the symmetry operator is just some dynamical brane. And by that, all I mean is it's coupling to the local fluctuations of the metric. So you can do this in Euclidean quantum gravity and Lorentzian. It all kind of goes the same. Okay, now you can use that to actually argue that there aren't any global symmetries. There are caveats and loopholes to this statement, but this is qualitatively true. So basically, you start with a bulk operator, which you think might be topological, push it into the boundary. It then defines some topological operator in the boundary CFP. But we just argue that everybody of this sort, when you pull it back out, has a tension. This is a contradiction. So you can't have this thing not coupled to gravity and then all of a sudden coupled to gravity by the end of the operation. There are subtleties to this. For example, it could be that you can't fully pull it into the bulk. There could be a flux tube attached, all of this sort of stuff. It doesn't affect the main argument that this thing is picking up attention. Yes, please.
In this scenario, actually the previous scenario where you have CMTFT, what does gauging or orbital in the CMT look like in the bulk ADS?
Well, so in some cases, it just corresponds to us changing the boundary conditions for the CMTFT.
Yeah.
So you take the bulk fields and you just change what the profile, what the boundary conditions for those are. So for example, a classic example is like take a one-form symmetry of n equals phi, where you have B wedge dc times n. You could switch from B equals 0 to C equals 0 on that. And that will switch you from, say, having like SUN gauge theory to SUN mod the n gauge theory. And then you do more complicated iterations on that thing. Yeah. So that's a way of us gauging one of the symmetries. Now, more generally, I don't know. So for example, there are certain lattice models we can talk about doing pretty complicated things with gauging a non-invertible symmetry or something like that straight in the lattice model. I don't know if any of that makes sense when you start including gravity, because the lattice you want to talk about is fluctuating anyway. So I just don't know if it makes sense. So
okay. And the second question is, so in this no global symmetry argument, you do not require the presence of a black hole?
No. No black holes yet. There will be black holes in just a moment, in case you wanted black holes. So I'll give you some black holes. Okay.
Like any optimization will move something from the boundary, it's impossible something from the boundary.
Yeah. So you can start with the operator in the CFT. And so what we're using is what's called like the extrapolate dictionary to say like, I want to tell you about how things are going and get close to the boundary and pull it back and forth. So I can start with my favorite global symmetry operator in the boundary CFT and say, tell me what it is in the bulk. There's actually a corollary to this, is that every time somebody claims they have an interesting global symmetry in the CFT, they're predicting a dynamical brane object in the bulk ADS. Some of these are branes people knew about already, but in many cases they're totally new weird things. Yeah. Okay, there's a loophole to what I just told you. Here is the loophole. Suppose I come along and I just say, I declare this is my theory of the world. It's everything I told you about before, and I've just decided I'm going to add a TQFT. This is my new worldview. Here is the partition function. Does anything go wrong? This would immediately violate the assumptions I made on the previous slide. Why? Because I have a TFT operator. I just push it back and forth. It's clearly topological. What's going wrong? So what happened to our nice argument? I'm going to argue that this can't happen. So in other words, we're going to repair the loophole. And the operator I'm going to refer to from the TFT is going to be called script T for topological. And I made it dashed here to indicate that looks like it's topological even in the bulk. Yes, please.
Is there a way of thinking about the loophole that like previous slides didn't account for -1 form symmetries?
-1 form symmetries can be accounted for. It's not quite the same argument with smearing.
It sounded like you were saying the problem was that there's like a space-time filling TQFT.
No, that's not, so minus one form symmetries can also be dealt with. It's not a smearing type argument. It's instead saying that the field profiles are jumping as you go from one. So it turns into a domain wall in the bulk. And then the field profiles are jumping from one side to the other. You say, I want to give you a domain wall, but it has no tension. That sounds crazy. So that's the flavor of the argument for the minus one form symmetry in particular.
What makes this different? Having
Oh, this could be any, I mean, I could give you my favorite TFT of whatever. I mean, give me your favorite TFT. These topological operators don't have to be space-time filling in the boundary CFT. Anything you want. So that's why it's a different problem. All right, so let's talk about that. How much time do I have? All right, yeah, that's fine. It's really hot in here, though. I'm sorry. Okay, so let's first recall how it works with just gravity. So now I'm going to switch gears a little bit. Everything I'm telling you works also in Lorentzian signature, but it's a little bit cleaner to set up the whole style of argument and faster, given the heat. That's good. For doing this in Euclidean ADS CFT. So Euclidean ADS, what is that? That's just going to mean a ball. And it has a boundary, which is a sphere. You can make it more complicated. It doesn't have to be, say, a ball. It could be anything you want that just locally looks like, say, a disk or something like this. And then you decide what it's going to be, the boundary manifold that you can. And okay, it's a little bit of a loaded statement. The idea is you have a source in the boundary theory, and then in the bulk, you have some boundary conditions that approach what you want to talk about for those sources. Okay. Now, more precisely, it's not just ADS. There's actually all these saddle point configurations. So if you want to do a slightly better job in talking about gravity in there, it's not just anti-de Sitter space. You look at the kind of field equations of motion and you find local solutions, and then you start summing them. These are the so-called saddle point configurations. The main constraint we impose is that whatever you do for these topologies, it still has to look like the same manifold at this boundary over here. And you can impose your favorite tangential structures and all that. That's up to you. Now, here's a nice statement. You can calculate expectation values for symmetry operators. Slightly a physically weird thing to do, but you can do it. Both from the kind of boundary CFT point of view, like so. Insert the thing into all your correlation functions and so on. Or alternatively, sum over all the saddle points with this thing inserted, this U tilde that we were talking about previous. And then basically the symmetry operator can wrap, say it's a product of two different spheres, it can wrap either the S3 or SQ, something like that. I'll just focus on S1 times SD minus 1. That's the simplest case, but a lot of this goes through for the other cases as well. Now, in this case, there are two nice saddle point configurations. One where you have a circle fibered over some ball, SD minus 1, and another where you kind of flip the roles. You have a disk, basically, ball associated with S1. Sorry, you cut it, yeah. And then you have some D sphere minus 1 over this. This is the Euclidean signature version of saying that we have a anti-de Sitter space and we put it at finite temperature. And alternatively, that we have the black hole we want. It is a so-called ADS short shield. So no charges or anything like that, just black hole background. And the point is that there is some minimal finite size sphere over here at this point here. This is associated with in Lorentzian signature where the outer horizon of the black hole would have been.
Sorry, what's that saddle?
Oh, it means you take the Einstein-Hilbert action and you find the equations of motion. And you find two different solutions given the boundary conditions. These have two different topologies in the bulk. So they're qualitatively just different things. So an observer living in the bulk will be able to tell the difference. But these are two different things that could happen to you when you solve the equation of motion. There's no guarantee that when you solve the equation of motion, you're going to get a unique answer. Right? So these just happen to be the two dominant configurations. There are many other saddle point configurations I'm ignoring, but they're all kind of subdominant and not going to play the big roles. Okay, so who wins? You can actually evaluate by looking at the action, just for the gravitational case again. And you get this thing like this. It's proportional to the black hole area that we were talking about. And then depending on the size of the outer horizon for the black hole and the size of the ADS radius, one of the two will win. Okay, so if the black hole is big enough, then it dominates. And conversely, if ADS is hot enough. Okay, and this is non-perturbed. So this is a very clear example of fluctuating topologies. Now, why is this interesting from the point of view of what we've been talking about? Well, you can wrap a brain on the minimal cycle, but actually the cycle that you have in the bulk changes depending on what you've done with the temperature, right? So in one case, we had thermal ADS, and in one case, we had this black hole background. So if I gave you a zero form symmetry operator for the CFT, then in the black hole background, it could wrap the outer horizon. But in the thermal background, there is no SD minus one for it to wrap, and it all shrinks away. So the saddle points kind of know or are informing us about how topology is messing up our symmetry. Okay, so in thermal ADS, nothing happens. In ADS Schwarzschild, the brain can wrap this minimal cycle. Okay, there are many examples where you can actually use this to calculate, say, the tension of this object. Maybe I'll skip that in light of the time because I do want to get to the argument about what goes wrong. So these are some examples that we worked out. You can figure out the tension. Very nice. I'm going to skip all of that. Okay, let's go to TQFTs versus gravity. So we're going to take the setup we just had. We're just going to add the TQFT into the game. Does this produce a contradiction? Okay, so obviously I have to tell you what I mean by the rules of the game now, because this is not just the straight ADS CFT correspondence anymore. I've now added some new ingredient in the bulk. I must be doing something on the boundary. I'm going to make a couple of mild assumptions. We're going to assume that the TQFT field only know about gravity in the sense of topology. And we're going to also assume that there's at least one TQFT operator T, such that when I calculate an expectation value for it, or something involving it, I get something different from just the quantum dimension. So it picks up some kind of non-trivial answer. Okay, I think this is pretty mild. If you don't like it, this is where you can complain. Okay, so here's what we're going to do. We're going to have the TQFT in the bulk. Now, this thing knows nothing about gravity. That's our assumption, right? We, of course, know many TQFTs that have their own edge mode systems. Could be gapped, could be gapless, who knows? It's just some other system. I'm going to call it QFT extra. It's living on the same manifold as the CFTD, but it has no correlation functions with anything in that CFT. It's completely decoupled. Not even at the level of, topological global forms, just absolutely, totally decoupled. So what's going to happen? Well, we can calculate the partition function over here. If I insert that topological operator, it has nothing to do with the CFT, so I just did this. And over here in the bulk, right, I have this sum over all the gravitational saddles, and I have to talk about the TFT being evaluated on all these different choices of saddles. Here's the question. Does this thing here, the bulk partition function, equal the boundary partition function? The answer is going to be no. How come? Well, we're assuming that we have this magical T that has a VEV in at least one of the backgrounds, and it only has a P cycle, say, in one of them. Sorry. Yes. Who doesn't care? Yeah, exactly. It doesn't. No. That's. I'm going to throw the question back to you. How would you like to define the gravity plus TQFT system? No. Like the closest thing you could think of is to say, well, I've just given you an action on these two things. There's clearly some edge mode system for the TQFT. So yeah, so indeed, what we're going to argue is that you sum over the saddles, and indeed, you're going to see that the bulk clearly cares about it. The boundary system doesn't. That's going to be the contradiction. So you've already kind of, like, if you don't like that, this is the closest we can come to saying, like, this is what you could possibly mean by having TQFT with gravity.
Better.
All right. Yes, please.
I don't understand the assumption of expectation. Is it saying that it's not equal just if it's equal or
no, it's basically saying that this T can wrap a non-trivial cycle, and you can get an exit. So if everything can just like shrink off to a zero size manifold, then all you're going to pick up is the quantum dimensions of the topological operators. We're looking for something that has a little bit more bite than that. So that's why we're making this assumption. Okay, so as John has already said or complained, I don't know which one. Yeah, this is what you get from the gravity side of things. Why? Because there's two different saddles. Clearly, they're going to give you different answers. One is wrapping the bulk a bulk topology cycle. The other one is not. And what's happening here? I'm actually varying. You can view it as varying actually the ADS radius. You keep the temperature totally fixed in the boundary CFT, and all I'm doing is if you like changing the number of large n degrees of freedom. So I'm assuming I have some kind of continuous family of CFTs where I can kind of dial that. Okay, here they are. Here's the two different topologies. You get different answers. Okay, so is this true? was already anticipated. No, it's not. One of them depends on the bulk saddle, the other one does not in any way. That's a contradiction. Okay, so what can we conclude from this? Well, it didn't factorize. There must have been something wrong with our assumption about the CFT being totally decoupled from this extra field theory sector. Okay, and the TQFT is not decoupled. Now we can just run the same argument we had. So actually, if we really had a CFT like this and we had a bulk ADS, this was actually just some other piece of the CFT that we forgot about. We were being silly to forget about it. So then we can run the argument I was telling you about earlier. We start with a boundary operator, smear it out and all of that, and we pick up a brane that has a tension. What does that mean? That's actually a much sharper statement. That means that there's some local source for the stress tensor from the TFT. That's a perturbative coupling to the graviton. So we went from having something that was totally decoupled to saying, well, decoupled, but only non-perturbatively due to some saddle point configuration. And now I'm saying something even more violent has happened. TFT fields actually know about the metric at the level of linearized fluctuations. So far worse. Okay, so this actually happens. Sorry, I should have said eyeball, but okay. So this is the example I was telling you about earlier with one-form symmetry. This is the kind of famous topological term that controls the one-form symmetry. You pick the boundary conditions here to get SUN versus SN1CN, or your favorite thing. From the point of view of gravity in ADS, what are you getting? These things both have kinetic terms. So it's kind of trivially satisfied in all the stringy examples, which is, I don't think why anybody cares too much. The point is that you had this topological filter, and then you added kinetic terms into the system. It's not like I forced it. It was just there from the start. Question is whether you could have gotten away with not even having this to begin with. Okay, more abstract TQFT. I don't know what to do here. So the point is that the general statement I gave you should apply very broadly. Take your favorite TQFT, add it in. If it can consistently decouple to gravity, the claim is that there's some linearized fluctuations to the metric and all of that. What does that look like in practice? I know how to do this in certain examples, obviously, but if you give me the fanciest TQFT you guys have been talking about, what does it look like? I don't know. But that's an interesting question. Okay, so let me just sum up because it's late and hot. Okay, so TQFTs are in the swampland. All that means is that there is some coupling to gravity. It's, for practical purposes, pretty negligible, but it's there. And the kind of idea was to look at how bulk saddles and summing over them kind of gets in the way of boundary factorization. Kinetic terms and more abstract TQFTs, I think that'd be interesting to figure out. And can we make sharper bounds on the kind of biggest gap that you have? I told you it was the Planck scale, but actually in practice, it's usually a bit lower, quite a bit lower, actually. There's some way to argue universally about what this kind of universal sharpening the bound. I'll stop there. Thanks again.
So, gravity itself is topological on the same line.
Okay, so in 3D gravity, I'm assuming that I have 3D gravity plus another TQFT. So yeah.
But I mean, you still get like a mechanical wave.
Yeah. So it worked fine in ADS3 CFT2. Things get a little bit weirder in ADS2 CFT1 and things like that. But I mean, ADS2 CFT1 is also weird. So anyway, yeah. Yeah, please.
I'd say everything I use from the size of it, something like another field that you want to be fuel there, which is the
Oh, no, that for sure can happen. That for sure can happen. What I'm saying is like TQFT that's valid all the way to arbitrarily high energy scales. That's all I'm saying. So yeah, of course, there's many beautiful TQFTs. I mean, like they're all over the place. That'd be insane. Like, the statement is more just like how big could that gap be? So in all the cases I know, right, there's a gap, and it's a measurable thing. You get above it, and then you start making fluctuations.
So you're all merging.
Yeah.
Correct. Last one. What about the SPTs, which are independent methodology?
I think SPTs would be. Oh, you mean are they in the swampland? Oh, I haven't thought about that one specifically. My guess is the same flavor of argument probably works, but I haven't thought about it too closely, so I don't want to say anything.
All right. Let's bring Jonathan again. Thank you everyone for coming.